Hello friends, in this particular video tutorial we're going to discuss limits and derivatives. Before going into what are limits, uh, what I would like you to revise is that plotting of some of the fundamental graphs and your concept of the rational functions. That is, basically just revise the functions and it will make your life pretty easier in this particular chapter. So let's move on. So this particular chapter is, I think, is been introduced first time, and it contains a subtly not very intuitive idea. I would like you to emphasize the importance of this chapter by stating the fact that all of the calculus in which is used in varied fields of mathematics and others like physics, especially physics and chemistry also, is based on this particular notion only. So let's first of all look into what is the concept of limit through an example. So here we have an example where a function hx is equal to x square minus 4 upon x minus 2. So from your previous knowledge of the algebra, you might be wondering that we can factorize x square minus 4 into x plus 2 into x minus 2 and cancel out the denominator factor, that is x minus 2, to obtain this particular expression, that is x plus 2. But I assure you that this particular expression is not identical, not at all identical to this particular expression. These two expressions represent different functions. As you might recall from your straight lines definition, that this is a straight line. If we take hx equals to y, so we have y equals to x plus 2 as this straight line, as this is a straight line, but this is a straight line, but this at this particular function. So at x equals to 2, what happens is that the numerator is equal to 0, as 2 square minus 4 is equal to 0, and the denominator is also 0. So basically we have a non-defined situation at x equals to 2. Therefore this point x equal to 2 is not in the domain of this particular function, as the function becomes not defined at that particular point. So basically what we have is that the function is similar to x plus 2 at all points not equals to x equal to 2, that is hx is equal to x plus 2 for x not equals to 2 and not defined at x equals to 2. So to make a graph like this, what we do is that we draw x equals to 2 and put a blank hole, that is this particular circle, at x equals to 2 to symbolize that the function doesn't have a value at this particular point. So as you see that as we approach closer to 2, the function has a value given by this function, this x plus 2, but as we go at 2, that is we reach on 2, we have the function as not defined. So basically what will happen is that we'll have limit at x tends to 2 hx equals to 2. That is, we say that as hx tends to 2 but is not equal to 2 from either side, let's say from this particular side, that is at x increasing side, we have the function given by x plus 2, and as we put values closer to 2 but not equal to 2, let's say we put 1.99, so we have the value of the hx equals to 3.99, which is very close to 4, as you may see. But if we further increase the value towards 2, still the value of the function remains closer to 4. It gets closer to 4 as we increase this particular x, and we can go further closer to 4, but it will never reach 4. So basically limiting process is putting the value of the function at x close to this particular point, that is when x is approaching 2 but is not equal to 2, and finding its value hx at that particular x, that when x approaches 2. So basically limiting process involves getting closer but not at that point which is specified here. Okay, so after this, let's move on to another example in which fx is defined as 1 for x less than or equal to 2 and 2 at x greater than 0. So in this particular expression what we see is that since the function is defined for all x epsilon r, however the function has the value which jumps from y equals to 1 to 2 as the value of x reaches uh, x reaches 0 from uh, as the value of x increases from 0 to infinity. So basically what we'll have is that in this particular expression also we'll have limit x tending to 2 minus, that is when x approaches from the negative side, that is we have x approaches 0 from the negative side, that is we have the value of x equals to minus 0.01 or say minus 0.001, or you can take as small as a value as you want. So if we have x approaching 0 from the negative side, then the value of this particular f, that is fx, is equal to 1, and when the limit of the expression tends fx from the positive side, that is from this particular side, that is we take the value of x equals to 0.01, 0.001, or say 0.000001, we have fx tending to 2. So basically at this point we have two particular limits, one when you approach the function from the negative sign, and one when we approach the function from the positive sign. So basically this is the idea of limits, and just keep in mind that we are approaching to the point, to the value which is mentioned here, and according to this sign, so basically this is the approach site, and this is the direction approach direction. That is, if we have this as positive, then we'll move from this direction, and if we have this as negative, then we'll move in this direction. So after we have looked into what is the basic idea of limits, let's try to manipulate and understand how to work out various other limits. So to work this out, what we'll do is that we'll take two functions f and g, who such that both of its limits exist when x tends to, let's say, a. Let's here also say a. So we have both these limits existing. Then the first expression says that when the limit of fx plus gx as x tends to a remains equal to limit fx as x tends to a plus limit x tends to a gx, and the value of the function fx minus gx as limit as x tends to a is also equals to limit x tends to a fx minus limit gx as x tends to a. The second particular point says that if uh, the limit of f into g as x tends to a is equal to limit fx as x tends to a and limit gx as x tends to a. Here there's an important point to note. That the limit of fx as x tends to a and limit of gx as x tends to a exist, and it's generally a misconception that if limit f dot g as x tends to a is also equal is existing, then this particular property will hold. But this is absolutely wrong. If this particular expression holds, we cannot absolutely say that this particular property will hold. This is absolutely wrong. The third and the last property says that as limit fx upon gx as x tends to a is equal to limit fx as x tends to a upon limit gx as x tends to a. So this particular expression holds when gx is not equal to 0 at x as x tends to a. Limit as x tends to a. This particular thing should not be 0. This particular expression won't be defined. So to work out a simple limit by using these particular laws, let's say we have this particular limit to solve. So to solve this limit, we need an identity that x raised to the power n minus a raised to the power n is equal to x minus a whole into x to the power n minus 1 minus x raised to the power n minus 2 into a plus x raised to the power n minus 3 into a square, and so on till a raised to the power n. And here we have n minus 1 raised to the power n minus 1. So this is the particular expression which we'll use in this particular limit. So to find the limit of this particular expression, what we'll need is we'll divide both the sides by x minus a, and as x is not equal to a, we can just cancel this particular expression, and to find the limit we'll introduce this particular expression here, and we'll have x minus x raised to the power n minus 1 minus x raised to the power n minus 2. Okay, we have pluses here, I suppose I was mistaken here. So we have the expression as this, and we'll have this particular expression to a square plus a raised to the power n minus 1. Now we can directly substitute a here as the function is defined at particular point. So after substituting the expression, we'll have a raised to the power n minus 1 plus a raised to the power n minus 1, and this will continue till n times. As you can see, we have 1 here, and we have a raised to the power 0 here, so we have 1 here. We have first this is expression number 1, this is expression number 2, this is expression number 3 till we have n. So we have basically n a raised to the power n minus 1. So basically the expression comes out to be n into a raised to the power n minus 1. So this will be the particular limit, and through by solving this, there are 2 points to note. First of all, use of rational function is of utmost importance, and identities are pivotal towards solving. So basically use rational identities. Second thing is that just if the function or the thing occurring after the limit expression has value, if limit has value at x equal to a, then directly substitute. If limit has value, that is limit exists at x equals to a, then substitute x equals to a directly into the expression of occurring after limit, because if the limit exists, then we'll have the limit as x approaches from a minus and limit as x approaches from a plus to be same.